Good morning, everybody, and I hope everyone's hearing me on our second seminar today for our analysis of test methods for waste and environmental recycling industries. This is the second talk of the day. And before we start, just a few little things. For questions and answers, please put these on your screen and we will answer all the questions at the end of the talk. Also, please fill in our questionnaires for some feedback that you'll also find on our Q&A portal. Today's talk on analysis of waste and other unknown materials by XRF is given by myself, Phil Russell, and will be joined during this talk by my colleague and application specialist, Gary Smith. So the agenda for this talk is looking at the issues for waste analysis, what methods are typically used for elemental analysis of waste, and then concentrating on waste analysis using the Rigaku XRF series of instrumentation and a fair bit on sample preparation as well. And then we'll have a quick summary at the end. So looking at what are the issues for waste. Well, we're not talking about refuse that you throw out in your bins from domestic waste. We're looking at industrial waste. We're looking at liquids, slurries, pastes, solids, pretty much anything you can think of. In particular, waste oil, which is a large component of the waste industry and is a large area for analysis. So looking at the techniques that are typically used out there, we're looking at sort of dip tubes, which are used out in the field to quickly ascertain whether a particular compound or material is present. It's qualitative only and has limited applicability. We're also looking at other techniques like titration, where you can use this for a range of compounds and elements. However, sample preparation is needed and can take some time, and it is a little bit limited in the range of elements it can measure. ICP, AAS, is a major technique used for the analysis of wastes, and it is typically a regulatory requirement. However, it does require extensive sample preparation, so time to get your analysis can be elongated. Then we go to XRF. XRF has the benefit that you can do the analysis with little or no sample preparation. It has a wide elemental range, typically covering the elements required in the waste industry for analysis and regulatory purposes, and therefore is an ideal technique and the one we'll concentrate on today. So, looking at XRF, the instrumentation, there are a number of different types of XRF systems that you can employ. There is a EDXRF and WDXRF. EDXRF is energy dispersive XRF, and there are two forms of this. One is a direct excitation, where an X-ray tube is used to excite the elements in a sample, and a detector is then used to detect those elements. This produces a lot of background in the analysis and can limit sometimes the levels of detection that you can achieve. An indirect type of analysis uses a slightly different approach. It uses a secondary target which polarizes the X-ray beam, and a little bit like sunglasses, it removes the glare. So in this case, it removes the background, and therefore is an ideal system when measuring waste, which tends to be all light matrix and materials containing high organic material, and this is an ideal area for a polarized secondary target system. WDXRF is a slightly different technique. It's a wavelength dispersive XRF, so instead of detecting energy, it detects photons as wavelength. It is a much larger system requiring a much more powerful X-ray tube, and it tends to be floor standing. However, it has tremendous sensitivities for key areas of the spectrum, and in certain areas, it is the regulatory choice for certain types of analysis, and we'll look at that later on. What are the issues for waste? Well, one of the things is we really don't know what's in it. It can be a solid, a liquid, it can be multi-phases, it can be any element or compound. It will also usually have a highly variable organic content. But in most cases, we can ascertain roughly some ideas on what's contained within the material. Although with XRF we can only measure from sodium to uranium, we can't look at the lighter elements. So therefore we have to provide some information about what the non-measurable component of a sample might be. But we do know sometimes whether it's a solvent, whether it's an oil, whether it's aqueous phase, and this information, it will be important later on in giving the information to the instrument to help in our analysis. So what techniques are best for elemental analysis? Well, XRF tends to be the best choice, and the reason is it's the fastest result turnaround. It has the least sample preparation capability, it's relatively low running costs, but the performance will depend on the applications required. So you have to look at your data quality objectives. What is it that you actually need from the analysis, and then choose the instrument that best and most appropriately fulfills that. So one of the areas immediately you need to ask is, what sort of accuracy would be good enough? Well, with this, we must ask the first question is, what is the problem? Well, it's the matrix and the representativeness of the sample. Generally speaking, waste is a highly heterogeneous material, and it is difficult to get a representative sample. So therefore, with accuracy, we need to take this into account. And so we're looking at typically an as received sample, a plus or minus 20% relative error on the analysis is usually an acceptable approach when you're looking at heterogeneous wastes where many samples will need to be taken in order to ascertain the true bulk analysis of the sample. And so therefore, what we need to actually start looking at is where this actually fits in with the scheme of things. So looking at the matrix, therefore, we need to understand a little bit more about the matrix. So a little statement, waste analysis is a compromise between the speed of analysis and the throughput of samples and the accuracy and precision that can be achieved to meet any particular regulatory or process control requirement. Generally speaking, liquids represent a reasonably uniform matrix. And unless they contain solids, they usually produce a relatively accurate analysis. However, with solid waste, unless some significant sample preparation is done, and as received sample being very heterogeneous, the analysis and the precision and the accuracy will be less so. So in the little pictures below, you'll see from left to right a typical sample in a sample cup of a solution, and this represents a nice homogeneous solution and is easy to analyze, and therefore the result you get from it is going to be fairly accurate and you can rely on it. As you go from left to right, you go through a series where you might get a biphasic sample where you've got oil sitting on an aqueous solution. You might get a biphasic solution with sludge settling, or you may even get largest particles that may settle out during the analysis. And if you'd been clever and looking at the little picture on the right hand side, you'll have seen a separation of what looked like a homogeneous sample at the start of this slide, but by just now you'll have seen it separated out. And if you get this sort of thing during analysis, then the result will be altered, and therefore the accuracy of the analysis will not be as good as could be. So these are things you need to take into account when you're producing samples for analysis by XRF. So for looking at the analysis of different matrices, you're looking at liquids and sludges. They generally speaking are a light matrix, and XRF can correct for the presence of aqueous and organic material in the sample, but if there is settling during the analysis, then you have to take this into account. So generally speaking, a fast analysis will minimize any settling errors and therefore provide you with an accurate result. There are other techniques that we'll go into in terms of sample preparation to avoid this sort of thing happening during analysis. Solids, however, don't represent this problem. There's no settling out during the analysis. And therefore you have the consideration to looking at mainly heavy elements in these materials. You're looking at toxic heavy elements being present, and for these elements, generally speaking, the analysis is reasonably accurate and can provide an overall bulk analysis. However, when you're looking at light elements, i.e. phosphorus, sulfur and chlorine, which are important elements in a waste analysis, you need to use appropriate methods in order to actually ascertain the best analysis of these, and usually some form of sample preparation is required to reduce what might be large chunks of very heterogeneous materials to a finer particle size so that they are more representative of the whole in order to get the best analysis, certainly for light elements. So just looking at the table at the below there, you're looking at two different types of element ranges. You're looking at sort of regulatory elements where you have heavy metals such as chrome, copper, nickel, vanadium and zinc. And you're also looking at the volatile toxic metals as well, which include cadmium, mercury and thallium. And for these elements, you typically get a fairly good analysis because the way XRF works is you can get a good bulk analysis from a solid material. However, other important elements like process control elements like halogens, phosphorus, sulfur, you need to take appropriate sample preparation action in order to get the best and most reliable analysis for these results. So looking at the sample preparation tools you can have for solid materials. Here we're looking at different types of techniques depending on the type of solid material you're looking at. So for hard solids, that are brittle, you can mill these to a fine powder and compact them. So here you can take a powder, you can mix it maybe with a binding material to produce a press, and this will then give you a consistent compact sample. If you have a soft solid waste, things like plastics and paper, this won't mill very easily. So you have to use cutting devices in order to reduce sample to a meaningful size so you can analyze it as a representative sample. And here the pictures show a simple kitchen milling device, a coffee mill type device, very, very useful, quite cheap to have. And this can reduce your sample size, or if it's a larger sample that you're dealing with, then maybe a more industrial size sample preparation, such as the large cutting mill that we have there, in order to reduce your sample size down to a meaningful level. You then need to compact the sample using some form of compaction device. And so for these sort of areas, what I'm going to do is I'm going to pass over to Gary now, and he's going to show you some sample preparation in some videos that we pre-recorded. So these are pre-recorded, and they're by Gary.
Hello everyone, and thank you for joining me here in the SciMed application laboratory. I'm going to demonstrate some sample preparation.
Phil, I believe Gary currently is muted. Is it possible to replay the video?
Yeah.
Sorry, everybody, just a small technical glitch. We're going to replay this video and make sure that you can actually hear what Gary's saying.
Yes, I did have it set up, but it seems to have lost its settings. Right, this should now work.
Hello everyone, and thank you for joining me here in the SciMed application laboratory. I'm going to demonstrate some sample preparation techniques which can be used to improve the quality of XRF analysis, particularly in the context of waste and recycled materials. The first technique that I'm going to demonstrate is pellet preparation using a hydraulic press and die set. The demonstration sample is a sample of carbon which has been recovered from waste automotive tyres. It's very finely milled powder and lends itself very well to pellet preparation, where a very high quality analytical surface is required. If necessary, we might add an inert binder to the pellet recipe. This improves cohesion of the sample and also prevents the generation of loose dust from the final pellet surface. Typical ratio of sample to binder is 4 or 5 parts sample to 1 part binder by mass. So here you can see we have a pre-weighed vial of sample and binder ready for mixing. This is placed on the mechanical mixer and mixed at high speed for typically 30 to 60 seconds to give us a completely homogeneous blend of sample and binder. As you can see, after mixing, the binder is completely incorporated into the sample. This is now ready for preparation of the final pellet. So we load the sample into the die assembly like so, with a dye pellet over the top to form the final analytical surface. These dye pellets are polished to a very fine finish to give a high quality surface. The dye is then placed in the press, and the pellet is pressed typically at 15 to 25 tons, depending on the requirements of the specific application. The resulting pellet has a high quality, flat, fine surface with no loose dust. It has fixed dimensions with known mass, height and diameter, all of which can be input into the XRF software to improve data quality if required. And that is press pellet preparation. Thank you. The next approach I'm going to demonstrate is manual compaction of loose powders. This approach lends itself well to situations where the sample doesn't press as a pellet. For example, this refuse-derived fuel, which as you can see is coarse, is not homogeneous, and has a very spongy texture which won't form a pressed pellet. In a situation like this, the solution is to weigh the sample directly into a liquid sample holder, like so. But the challenge here is consistency of compaction. As you can see, this sample is very loose, and the majority of the volume of this sample holder is actually air. This can lead to errors in analysis by XRF, in particular if we're using fundamental parameters with backscatter correction, which Phil will discuss later. The solution is simply to compact the sample using the manual press to achieve a consistent sample packing. This removes the entrained air from the sample. As you can see in this example, the sample volume has reduced by a factor of almost 3. And we now have a sample with consistent compaction, which has measurable dimensions for diameter, height and weight, all of which can be input into the XRF software to improve data quality. So that's manual compaction of loose powders. Thank you. I'm going to talk about analysis of liquids now. The first approach I'm going to demonstrate is direct measurement of liquids using a liquid sample cell. This is appropriate for samples which are relatively clean and don't have multiple phases that could separate during the analysis. The sample holder is usually formed of 2 or more molded plastic parts which trap a thin film window, usually made from polypropylene or mylar, to form the measurement plane or measurement surface of the sample. Assembly is generally very quick and easy. We simply trap the window between the 2 rings and push it through to form a flat plane measurement surface like so. It may or may not be necessary to weigh the sample depending on the application that we're working with. If, for example, we're working with a simple screening of sulfur in oil, then it may not be necessary to weigh the sample. If, however, we're doing a fundamental parameters screening, then it would probably be necessary to weigh the sample and give that information to the XRF software. Once the sample is in the cell, we simply put the cap on and leave it in a clean place to check for any leaks before we present to the XRF. We may also use a secondary cup to protect the optics from potential spills. So that's presentation of liquids direct in a liquid sample holder. Thank you.
So that was Gary just showing you some sample preparation techniques that we can employ for the analysis of various sample types in the analysis using XRF. So we now need to look at XRF itself and look at the way in which it actually carries out analysis. And in Gary's little talk on sample prep, he alluded to a number of different approaches. One of those is simply just using a classical calibration. For example, in the analysis of waste oils, where you take a suite of standards and you create a calibration for that standard matrix using specific analytes with known concentrations. This is a classical approach and would be applicable to waste oils where the matrix is known. However, there are other situations where the matrix is completely unknown, and therefore you have to have some form of mechanism in order to analyze that. And for this, we use what's called a fundamental parameters approach or standardless analysis approach. There are two forms of the standardless analysis FP approach. One is where you have an idea as to what the matrix is, so that you actually then understand all the elements and compounds that will be present in the sample. So, for example, a waste oil lends itself quite well because you know it's an oil and you can estimate maybe what that oil is, or it might just be an aqueous solution, in which case you know that the main matrix is water, and this information is then fed into the instrument and it can actually take into account what these elements are. However, there are situations where you don't know what the matrix is, or it could be a mixture of water, oil, solvents with all sorts of hydrogen, carbon, oxygen, nitrogen variations. For this, the instrument cannot be given the information, and therefore it has to have some way of calculating the components. And it uses this using what's called a scatter FP approach, where it estimates the background that's produced by the material, and from this it can estimate what's in the sample. For example, here we have an analysis on the left-hand side, spectra shown of zinc at 250 ppm. This is from a number of different types of materials, from diesel through to water, and you can see that the response is completely different depending on the matrix. On the right-hand side, however, you have what's called the scatter lines. These are the scatter lines in the background of the system, and they have a direct correlation to what is called the average Z, or the average atomic number of the matrix. And from this, it can estimate the actual unknown compound, and it uses this to correct for that compound, and it can be a range of all sorts of organic materials containing carbon, hydrogen, oxygen, nitrogen, all those things that XRF can't detect. And this is a very, very powerful technique used by XRF for measurement of waste samples. So looking at fundamental parameters and looking at the way in which this works, basically the model is a scattering FP model. It corrects for the matrix not seen by the spectrometer. It can automatically detect all the elements present and actually what we call deconvolute the information out of the spectrum so that it has intensities for all the elements it detects. You can then go one stage further, and you can actually then put in a similar material or a sample that you have known analysis of, and this you can use to correct for variations in bias that are seen by the spectrometer due to a particular matrix or the matrix form that you might have, or the amount of sample you're putting in. And this can actually be used in order to validate your analysis, in order to look at recoveries, whereby you spike a sample with a known amount, and what you're looking for is the analysis correlating to that amount. So here's some examples of the analysis using the scatter approach. We have a dehydrated cake here of material, and it contains all sorts of organic material. The effect of the elements such as hydrogen, carbon, and especially oxygen are quite dramatic, especially for light elements, and therefore we need to actually estimate this analysis. So in the tables below, you can see along the top, the first column, the first row is the analysis that we were expecting. This is coming from other techniques, and below that you can see what the estimate is using the scatter FP approach, which gives you an analysis very close to that that you would expect. If you look at the two other lines, you can see if we tell the system that the matrix is all carbon, we get one type of analysis, or if we say that pretty much the balance is oxygen, i.e. it's basically oxide materials and things like that, then we get a slightly different result. Neither of these two is correct because it's a mixture of both, and this is why the scatter FP approach is the approach used extensively throughout the software using the Rigaku EDXRF and WDXRF systems. So, for an example, we're now going back a little bit, and we're going back to the looking at individual instruments here. So we're looking at a waste oil, which is a large area of industrial analysis done for waste materials. And here we are looking just at a classical calibration. The calibration there shown is one for chlorine, and the little circles and dark blue diamonds show the corrections that the software is making for the presence of other elements and compounds in the sample. For this, we just simply create a standard calibration where we're just looking for basic elements within a waste oil, and for this we simply pour the sample into a sample cup, as Gary had been showing, and we actually measure this on a entry-level instrument, which simply just sets up a calibration and measures directly the sample from a standard calibration in a classical form. So here, for example, we're looking at just the inbound waste analysis coming from a tanker load, coming into a transfer station, and we might simply just want to know the sulfur and chlorine analysis and making sure it's within the expected specification. We also might want to actually have a quick scan for metals, which these instruments can do, and we have calibrations set up on these simply to scan for elements. It will not go down to very low levels, and this is just an estimate to give an idea to the transfer station whether there are any toxic metals that might be present which they were not expecting. So it's a screening technique. So for this, we're going to transfer over to Gary, who's just going to show us a demonstration of this. So over to you, Gary.
Thank you, Phil. So welcome back to the Apps Lab. We're going to do a quick demonstration now of rapid screening of incoming waste oil using the Rigaku NextQC benchtop EDXRF. This is a completely self-contained benchtop analyzer with a built-in processor and software and an integrated touch screen interface, which allows simple navigation through the software. We have here our waste oil sample, which we demonstrated earlier in the liquid preparation. I've preloaded it into the cell, and we're going to simply pop that into the spill protection cup and then load it onto the sample carousel. Close the lid, and then we're going to go over to a close-up view of the screen so that you can see what I'm doing in the software. So to set the analysis running, all I need to do is select the relevant application. There will be an icon here for each application which we've predefined. Enter the job details. Select the position on the carousel. I'm going to call this one Demo A. And then press the Start button to set the job running. This type of analysis, as Phil has said, is a classical calibration approach where we're calibrating using matrix standards. So these might be synthetic mixtures, or they might be examples of real waste with known quantities of the analytes that we're looking for. The most important factor, whichever way you go with calibration, is to ensure that the matrix of the calibration standards is as close a match as possible to the matrix of the unknown samples which are being analyzed. The typical measurement time for this kind of application would be of the order of maybe 60 to 100 seconds if we're doing a simple waste screening for, say, sulfur and chlorine in oil, or maybe more like 5 to 10 minutes if we had a suite of metals and screen for a suite of metals. For the purposes of this demonstration, we've cut the measurement time down to 20 seconds, just so that we can show you the cycle from start to finish. And if I go back to the close-up view of the screen and press the report button, we can see here that we have the sulfur and chlorine result clearly displayed on the screen, with a very useful pass-fail judgment feature which can be predefined in the application so that the operator has a quick reference to process specification. There's also a thermal printer which gives
the results are on paper which can be taken away from the instrument. So with this kind of setup, it may be possible to obtain an analysis within 3 to 5 minutes from receipt of sample, which is ideal for rapid incoming waste screening. I'm going to hand back over to Phil now, and he's going to continue with the rest of the presentation. Thank you.
Thanks for that, Gary. So moving on now, we're looking at materials and waste which would be far more complex. So we're having to actually employ higher power instruments that are going to actually be able to cope with the measurement of difficult materials, and where there is a requirement to get much lower detection limits of metals and other non-metals for possibly regulatory or process control requirements. So again, the sample could be a waste liquid or solid, and you require this higher performance requirement. And so the sample when presented to you could be a dark liquid. You've got no real idea of the physical nature of it because you can't see into it. It could be an organic solvent, it could be oil, it could be water, it could be a mixture of these things. It could have possible undissolved solids in there, very high levels, and it could be a solid waste like a refuse-derived fuel, and it could be very heterogeneous. So for this, we require a slightly more powerful approach. And for this, we can use either a Rigaku NEXDE system, which is a direct excitation system, or a Rigaku CG polarized system, which is the polarization system that we have for this. So in this area, what we're looking here is we're looking at using the scatter FP approach to analysis, where we want to actually ascertain the matrix as part of the measurement. And so the instrument can correct for that area, and you can use, for example, polarized optics to get very low background detection limit if that's required. So you've got a choice of techniques to go forward. It is ideal for difficult samples which are organic rich, light elements such as we see in the waste industry with oils, solvents, water, plastics, etc. Now, one thing you do have to do with this, in order to actually allow the instrument to calculate the density of the material, is you must have the sample weighed beforehand, and you also have to know the volume. And for this, in a sample cup, we simply measure the height of the sample before we do the analysis. And so this allows us to look at the non-measurable component. So to do this, we've got Gary set up here ready to do another little live demonstration for us, looking at the analysis of samples using the DE instrument in this case. So over to you, Gary.
Gary, you all good live on camera?
Okay, thank you very much, Phil. So we're going to move on to a demonstration of screening of more complex waste using fundamental parameters. The kind of materials that we'll be looking at here would be samples which are either maybe completely unknown liquids, or samples with more complicated matrices. For example, this refuse-derived fuel, which we were looking at in the sample preparation demo. This kind of analysis really requires the application of fundamental parameters and backscatter correction fundamental parameters, as Phil has already mentioned. So we would require either the NEXDE, the Rigaku NEXDE, or the instrument that we have here, which is the Rigaku NEXDE. The primary differences with these systems are a more powerful X-ray source and more advanced detectors for better quality raw data, but also quite critically the addition of an external PC, which gives us the processing power that we need to run these more complicated fundamental parameters calculations. So I'm going to analyze the refuse-derived fuel sample, which we prepared in the sample prep demo. I've loaded it into the cell, and we've recorded the weight and the height of the compacted bed of material. These dimensions are required for the scatter fundamental parameters calculation. So we place this in the carousel, I'm going to close down the lid, and then we're going to move to a screen view so that you can see what I'm doing in the software again. So the front-end interface is quite simple and intuitive to use. I simply select the position that I've loaded the sample into on the carousel. I select from predefined applications, which can be pasted up here as a pick list. I'm going to select for this one powder screening. And then the table on the right-hand side prompts for the relevant information that the app needs. So we're going to put a sample name in, demo RDF. I'm going to give the mass and the height to the software so that it can perform the scatter corrected FP calculations. And this process would be repeated for any other samples that I wanted to measure at the same time. And then just press start to commence the analysis. The typical measurement time for a full screening of this type may be anywhere between approximately 5 or maybe as much as 15 minutes, depending on the requirements of the application, in particular precision and limits of detection requirements. As it's not really practical to show that from start to finish, we're going to go to one that we measured earlier. So if I pull up the results display, I can scroll through my previously analyzed samples. And this is the same refuse-derived fuel sample which I analyzed previously. And on the bottom table, we see the calculated result for each component, along with an estimation of statistical error and detection limit, which these statistics are very useful because they tell us a lot of information about how relevant that analysis analyzed value is in the context of the analysis and the precision of the measurement. So if I scroll along these results, I can then look for any elements of concern. And like with the next QC, we have the facility to put in pass-fail criteria, which flag if an element is at a level of potential concern. So in this application, as an example, chromium is looking a little bit high at 160 ppm. And if I continue to scroll across, you can also see that there's quite a measurable amount of lead in there, 29 ppm approximately, against a limit of detection of just around half a ppm. So if this is an element of potential concern or an unexpected element, and we want to interrogate the data further, we can do a kind of sanity checking process on the results by actually looking back at the raw spectrum data, and we have the facility to go in and interrogate the raw spectrum data. So I'm going to jump to the spectrum display now. And I'm going to select the part of the spectrum where we would expect to see the analytical peaks for lead. And here I can see the theoretical marker for the primary lead line and the theoretical marker for secondary lead line. So if I zoom on this area of the spectrum, all of the theoretical marker lines are color-coded. So the lead lines here are all color-coded in red. And we can see quite clearly that we've got a solid match for lead L alpha. We've got a solid match here for lead L beta, and matches for some of the smaller side peaks around the lead L beta line too. So we could have pretty good confidence here that lead is genuinely in the sample at approximately the levels that the software has calculated. So that concludes our quick overview of fundamental parameters analysis. I'm going to hand back over to Phil now, and he's going to conclude the rest of the presentation. Thank you.
Thanks for that, Gary. So we're back now, just to finishing off our presentation. Whoops. We're now looking at possibly a case study, just going over some of the stuff that that Gary alluded to. In this situation, we have a waste coming from a buffer transfer station, and they're wanting to do a quick analysis of that waste to check whether the waste is what they think should be coming in, because they've done a pre-qual prior to this. They know roughly what should be coming, and so they want to do a very rapid screening. And in this case, they're doing it again by scatter FP, and they're doing a quick analysis. So this is the sort of result that you would get in real life. And when you're looking at the results going across the top row, and then you're looking at concentrations which they're expecting and have pre-qualifications for, so they're checking against these analyses. The system will also measure other types of analysis using what's called an ultra carry technique, using for wastewater, and this is particularly a useful area using the CG instrument, and I'll mention this later on in our talk. So when we're looking at the results, and we referred to earlier about what you sort of can get from the instrument in terms of accuracy and performance, well, Gary showed you can interpret the spectra. You can look for the peaks, so you can get a qualitative image to see whether the actual peaks exist in your sample, but also you're looking at detection limits. And here on the right hand side of the table are the typical sorts of detection limits on a routine analysis that you can achieve using this type of instrumentation. On the bottom screen here, you have a quick scan of what the peaks would look like for around about 5-6 ppm. And so you can clearly see at these levels, the peaks are clearly above background and very easily seen. So interpretation is straightforward. So the next thing comes is how easy it is to set one of these systems up. Well, it's very easy. We have a set of templates that are used by the instrument to start you off to actually set this up. And so typically these templates have a range of different types of materials you might want to add metals, alloys, filters, etc. But for waste analysis, typically we're looking at oxide powders, polymers, or liquids are used as the starting point in templates. And the one highlighted there is the scatter FP version. So it's very quick and easy to set these analyses up. So looking at unknown waste, again, we're looking at a scatter matrix correction type approach, and we want to actually then look to see how good this is against other techniques. For example, ICP OES, typically used in the industry, takes a little bit of time to do the sample prep, but the results usually are very good. So we're looking at the results coming out. If you look down the first column, this is the expected result. This is the result produced by ICP analysis, which we're referencing against. The next column shows you the results that we actually achieve using a scatter FP, and you can see the sorts of results from this typical waste are very, very good and match very nicely with ICP. As Gary pointed out, the printout from the XRF gives you an idea on the precision of the analysis. So we're looking at the statistical variation of the result, and also it's giving you an estimate of the limit of detection in that particular sample. So you can actually validate that result to see whether it is meaningful and well above background, so you can have some sort of reliance on that result. We now want to move on to just looking at the way in which XRF has been used in the industry and by the regulators, and looking at some of the methods and the standard international methods and protocols that are available in the marketplace. So here you have SEN methods currently available for the analysis of solid waste, and this is solid recovery fuels. And there are two SEN methods. There is 15410 and 15411. The first one gives you a basic analysis of some of the elements, and 15411 gives you a more detailed analysis. Both of these methods use ICP results and ICP methodologies. However, within both of these, it recommends the use of XRF as a screening technology in order to actually assess which of the ICP method routes that you should be using. So ICP and XRF complement each other very nicely here. For chlorine, fluorine and bromine, XRF is currently not a SEN method used, but the SEN method there for various methods is available. SEN is also now developing a dedicated XRF technique, and it's a proposed method, it's 22940, and we're looking forward to this method being available for all users by XRF. Now moving on to liquids and the methods that might be available for that in the international marketplace, and these have been developed for a much longer time. And there are three typical methods that we're using here. One for WDXRF systems, and this is the first part for WDXRF, and one for EDXRF. All these techniques use a calibrated route, and therefore the majority of wastes for metals especially is now done by XRF using these methodologies. So the first methodology we want to look at is IP503. This is simply for chlorine and bromine in waste oil, and it is a WD-XRF system, and you can see an image of the Rigaku Primus 4i system. This is a typical high power wavelength dispersive system that this methodology is used for. It is a internal standard reference method, and it's built up using synthetic calibration standards to produce calibrations, and you can just see the software and a typical calibration there for chlorine being made up ready for this method. You can use the NEXCG for this with a modified approach, but it would be a modified method, but XRF is available for this for both ED and WD. The next international method is IP593, and this was developed specifically for wavelength dispersive systems for the measurement of burner fuels in order to meet compliance, in order to allow burner fuels to be recycled from waste materials into a product. And this is the conformance that is required, whereby all the metals typically there, both the heavy metals and the toxic volatile metals, have to be within certain specifications in order for these materials to be sold into the burner fuels market. And you can see there the table on the right hand side, the typical ranges you're looking at. So they're all from sub ppm, from about 0.5 ppm to 20 ppm. So it's a very low concentration, narrow concentration range for most elements. Other elements such as lead, nickel and chrome, they are at slightly higher levels. And sulfur is always measured in these materials because it has to be measured in order for a matrix to be run. But then, generally speaking, they're wanting to do very low sulfur in these materials because we know we don't want to be burning oils and things which have high sulfur content. So these are the ranges of methods that are available. We're now moving on to the EDM ASTM 6052 method, which is one of the oldest methods available. This uses two approaches. It can use either a classical calibration, setting up using standards, or now more recently, there is a standardless analysis fundamental parameters approach using modern fundamental parameters analysis to the analysis of using this technique. And either of these can be used. What this does is it combines all materials into a common matrix. So it can be used for multiphasic solutions, sludges, very inhomogeneous materials, and also when you've got particle size, particles settling. So just a quick little review of how this works. It transfers basically.
We need to wrap up in 1 minute, please.
Yep. It transfers it into one single matrix, and it takes 15 grams of alumina, 5 grams of sample, mixing it with some balls, and if you wish to look at the actual reference to this, you can see this on the JAS reference there. The sample is just simply placed into a sample cup, and it's easy to transfer into the cup. You don't need to compress, just tap lightly and measure. And finally, just looking at the technique I referred to earlier, this is the ultra carry technique where you can look at parts per billion levels in groundwater and discharge water. And this uses a small sample placed onto a sample disc and dried. This is about 200 microliters put onto these special cups. And the performance you can get there using a WD or an ED-XRF system is in the parts per billion level. And this is a pre-concentration technique. So in summary, we're looking at using a fast QC measurement for waste oils, such as the QC. We can go on to more complex materials where you use the DE and the CG, or you can look at regulatory compliance analysis for chlorine and bromine, etc., using a WD approach, or you have the ability also to do processed groundwaters by the XRF ultra carry technique. So in final summary, XRF is an ideal elemental analysis for waste as it handles many matrix forms and levels of homo and heterogeneity. Sample preparation can be as received, or a sample preparation can be carried out in order to produce better results. International norms are available. The performance meets industry and regulatory requirements in many instances, and it's easy to use and very cost effective. And thank you for your time.
Thank you very much, Phil. Well, we have got a few questions. Obviously, we're mindful of time. We've got about 5 minutes before we need to cut off ready for those who want to attend the next webinar. First question actually is about referring to the earlier part of your presentation regarding the sulfur and chlorine on a QC. Do you need to calibrate the instrument every day like an ICP?
No, you don't. The great thing about XRF is its inherent stability. So typically calibrations are set up in advance and they remain in the system and relevant for many months, if not years. There is an ability to use a single stable monitors to monitor your calibration to do drift correction, but this is just carried out periodically, maybe once every month or so, just to check. But the inherent stability of XRF does not require that sort of protocol.
Thank you, Phil. I've got another question that's going to be for Gary here, so over to you, Gary. How easy is it to set up the kind of applications you were talking about, particularly the FP ones on the NXDE?
Okay, so the Rigaku software uses a template system, and this helps to guide the user through the setup process. So it can be as simple as using default settings and then just selecting the components that you want. If you wish, I can go into screen view now and actually run through it in about 30 seconds to a minute.
Well, I'll tell you what, if you want to set up your screen view, and I'm going to ask another question that Phil can probably answer, and we can come back to you just to optimize our time. So we'll come back to you in a second, Gary, if you want to get your screen ready.
Absolutely.
Phil, how accurately do you reckon you need to measure the height of the material within the cup?
It's a good question. Typically to around about sort of 0.1 of a millimeter, 0.1, 0.2 is more than enough. It is an estimate in most times, and it can be sometimes difficult, especially if it's a very clear solution or a clear liquid. So if you've got a cup that has a height of maybe about 15 millimeters, then anywhere between sort of round about sort of 0.1 to 0.5 millimeter accuracy is all you need.
Okay, thank you very much, Phil. Gary, we haven't got your screen.
I'm ready to go when you are, Paul.
Okay, yeah, okay, cool. So over to you, Gary. If you want to show what you want to show on the screen, the screen is live.
Sure. Okay, so quick run through FP application building. The way the Rigaku software works is we have this flow bar down the left-hand side, which acts as a software wizard, and we have a set of templates which predefine some of the information that's really important to the analysis and calculation. So the templates available are shown here. They're categorized by material. So for example, if I want to set up a scatter corrected liquid application, I just select this template SQFP liquid DE, give the app a name, and the application template opens with an active periodic table, which we can just use to switch on and off the elements that we want to look for in the sample. So I can go through and switch on the elements that I could expect to be present and switch off the elements that I would not expect to be present in the sample.
And I take it the elements in yellow are the ones you will have in the sample. The ones in green are the ones you just don't expect ever to be there.
That's right. So the color coding is yellow is switched on and green is switched off. There's then some requests for information about what type of sample film you're using in your sample cup. And again, this is all predefined in pick lists. So if I want to do a liquid protection cup, I select Proline 2. The typical mass and height can be predefined for the scatter correction, or we can set those to manually input. We can override that that predefinition.
I suspect for the sake of time, Gary, we probably can't go through too much of the detail.
And then output information is just how we want to report the final results. And this is where we can put our upper and lower process limits in for our process judgment. And that's it. That would create as a basic application with out-of-the-box fundamental parameters in as little as 2 or 3 minutes. You can then refine from there, but to do the basics, that's all it takes.
Thank you. Phil, if you want to close the presentation.
Yep. So Thanks everyone for attending. I hope it's been informative, and obviously if you've got any questions or you need to know anything more, we're always open. Just send us through your emails and contact us, and we're happy to help.
Okay, thank you. And last comment, if you can find a minute to fill in our feedback form, it'd be much appreciated. Thank you, Phil. Thank you, Gary. And I believe the team ready for the NIR and Raman presentation are ready to go. So over to you. Thank you. Bye-bye.